So to know what tcache is, we have in the first order to know why tcache and what tcache is used for. So assume we have this memory with 5 allocated chunk. Assume this chunk is allocated, sorry. So then at certain point in the program, we free this memory like this. Whenever the memory allocator ask for memory again, so instead of extending the dynamic memory, we use this chunk. So how the allocator will know where it is located? So it will check this chunk. It will find out that it's not free chunk. Then it will check again this chunk. Then it will check again until it find the freed chunk. So as you can notice, this is bad approach. Why? Because the worst case scenario is to check all the dynamic memory until we find a free chunk, and this a lot of time consumption. That's where tcache ID came from. Why we don't make a little box here? So after we free a memory, we make an entry of this box here, point to the freed memory. Then assume we freed again this memory, then we'll make another link here which point to the free memory. So whenever the program is asking for a memory space again, we will search in this table and see where it's point. Okay, the first entry, we are going to use this block because this entry is pointing to this block. So we are going to delete the linking and reuse this chunk again. So that's the idea behind tcache, to reduce the time complexity for finding freed memory. Let's take a look how tcache indeed is implemented. Tcache is simply a table consisting two rows, the count rows and the heads rows. The heads rows is an array of addresses pointing to linked list of type tcache entry. We'll explain that later. And the count row is the length of a particular linked list. Tcache entry is simply contains two addresses. The first address is the next. This address is, as you know, in the linked list data structure, is an address who point to another tcache entry node. The second one is the key. The key is an address of the tcache itself, which means this tcache. We will use this key for verifying if this entry free or not. So as a demonstration here, let's take a look how counts and heads working together. Assume here we have 2, for example. Oh, let me 2. Okay, it means that the head will point to a linked list of length 2. Have 2 nodes here. At the index, let's say 4, 0, 1, 2, 3, 4, we have 1, so it will point to 1 node. Let's say here 3, it will point to 3 nodes. So this is how the counts and the heads working together. So as we said, tcache is an array. We'll have the count and the tcache entry which point to a linked list, as we said before. Of length maxbins. Maxbins is simply the numbers of chunks in our memory, the maximum bins in our memory. Why? Because we have to demonstrate all the memory chunks in our memory here in the tcache. So we have allocated here A equal malloc, memory allocator, B malloc 16, and C, D, E, F as well. So what happened to tcache? It will be not affected. Why? Because as we said before, tcache will change only if we freed a memory chunk. After performing the free operation here, we'll notice the tcache is changed. Why? Because we are caching the freed chunk in our memory, in the tcache here, to make it easier to access it later. So let's take a look in deep how we get this form. First, we freed B. B is of length 16 bytes. So we have to calculate the index of 16 byte size. So 16 minus 1 over 16, it will be 0 if we take the integer part. So it will be stored in the index 0. Then we pushed B to the linked list. We should not have missed the part of incrementing the count by 1. It was 0, now it will be 1 after freeing B. After that, we freed A, which is also of length 16 byte. It will be pushed here, and the head will point to the last pushed element. If you are not familiar with linked list, you have to study data structure and algorithm. And we also increment this by 1. Free F. F is of length 32. If we are going to find the index, we will calculate 32 minus 1 over 16. We will get 1 here. So the index will be 1. So we'll push F. Here's the F. And we will push also E as well, as you can see here. And every time we're pushing, we should not forget to increment the count by 1 to track the length of our linked list. Lastly, we push the C, so the head is pointing to the C node. We freed D as well, D of size 48. If we calculate 48, we will get the index 2 because 48 minus 1, 47 over 16 will get 2 point whatever, and we have this only node. So we have been allocated x, y, z of length of certain length. As we can notice, the tcache have nothing to do with this allocation because we didn't free them yet. Here is a little demonstration about reusing after free. Thus, we allocated 4 spaces, A for 16 bytes and B 16 bytes, C 32 and D 64. Let's look how the tcache in the memory look like and the allocated space. Here's the tcache. Till now nothing is changed. The tcache is still empty. And here's the space we've been allocated. A 16 bytes, B 16 bytes, C forget the 32 bytes, and D 64 bytes. Here we call the free A. Thus, the free A will first, as we said before, calculate the index, which is size of allocated chunk minus 1 over 16. You may ask why we subtract 1 here, because we are going to start from index 0, not 1. So we subtract minus 1 to get the integer part of this division. After getting the index, we'll check if the memory not already freed. How can we achieve that? Is by checking the key here. Okay, if the key is the address of tcache, then it's a free chunk. But if it's not, it's allocated chunk and in use, so we can free it. But if the key equal the tcache, we can't use it, and the compiler will detect double free, and it will throw probably an error. After we check the A, we push this node and we update the head of tcache and increment the count by 1, then pointing to the chunk here. And we can't forget to adjust the key equal tcache, and we don't have to forget to update the key to be equal the tcache, because next time if we are going to free, we have to add this flag to make sure this block is freed. Then we call the freed B. As we said before, also we have to calculate the index 16 minus 1, 15. We get the index 0. Check if the memory not freed. We check the B of 1, which means this B0. This is the next is the 0 here, and the key is B of 1. So B of 1 not equal the address of the tcache. It equal dummy data we've been used for in the allocation. So we can free it, then we can push it to our linked list, then link it with the remaining linked list, which is A alone in this case. And we add here 1, it become 2, and update the head. Here we reallocate again. So what will happen in this case? The program, we have 16 bytes. The program doesn't need to ask more space from the operating system. It will reuse its own predefined space, which is A and B. What will happen is it will calculate the IDX also with the same way, subtracting 16 minus 1 over 16 equals 0, and it will check if there is previous freed memory to use, with checking the count if it's greater or equal 1. In this case, it's 2. Now, after using it, we will subtracting minus 1 from here, and it will become 1. Then popping the front, which is B, and we mark key as null here because it's not read anymore, it's in use. And we update the head because we are popping B. But there is something we have to be aware of, that the next pointer is not clear and not checking if next makes sense. Here, the B's still have the previous data. Next is still pointing to A. But just in case, we freed the key. How can we take the chance exploiting the free and the allocation logic in the tcache? I'll ask you one question. What we override the next address of certain chunk? Let's take this scenario. We allocate A and B, then free them. This will result of linked list two nodes in the tcache with marking the key of address tcache, this address. Then the head will be point to the last pushed element. Then we overwrite the B of 0. So what is B of 0? This is B of 0. This is the B of 0, the next pointer. We overwrite it and make it point to another address, which is custom buffer. What is custom buffer? It can be anywhere in the memory as long it satisfies the writable condition, because we are going to write on this custom memory buffer address. It can point to stack, it can point anywhere as long it's writable. So here's the result. The B will point to, the head will point to B, and the BR next, it will point to our custom memory address. After that, we allocate with malloc 16 and malloc also 16. The X will pop the first element, which is B here, in the stack, because the head is pointing here, and Z, it will pop the B arrow next, which is B arrow next, which is this address, the custom memory address. So the result will be like this. This will be Z, and X will be this chunk. What happened here is we tricked the logic of free to get custom memory address instead of dynamic, the typical dynamic memory address, and we can have control on it with writable permission. Now we have control on our custom memory address on Z, and we can do whatever we want. At the end, thanks for watching and see you later.